Hi, everybody. This is Dr. Sassmore. It is Tuesday night. I'm not going to be able to be in class Wednesday morning, so I'm doing this instead and creating a recording. This is the lecture I would give were I sitting there. So I will post this to our Canvas page, to our YouTube channel, and you'll have this just like we were in class on Wednesday. I want to do derivatives. My derivative equation, limit as h goes to 0, f of x plus h minus f of x all over h is a pain in the butt. So I'd like to see if there are easier ways to do this. So I'm going to look at different kinds of functions and see if we can come up with some patterns and make some overall statements that will make our lives easier when it comes to taking derivatives. We're going to start with polynomials. So let's start with a polynomial of degree 0. That means we have a constant. If I asked you to graph this, this would look like a horizontal line. Wait a minute, what's the slope of a horizontal line? Most of you should be saying 0 right now. So that's a good idea that I would think that if I took any point along the line and I tried to measure the average rate of change at some point, I would expect that average rate of change to be 0. But we should check. If this is my f of x, f prime of x, using this same derivative definition, but what's f of x plus h? You plug in x plus h up here, you get a0. What's f of x? You plug in x, you get a0. So the top of this fraction is a0 minus a0. Wait a minute, that makes the top of that fraction 0. And the limit of 0 is 0 because 0 is a constant. Yay, that matches what I intuitively thought would be right for the slope of this tangent line. If I go from degree 0 to degree 1, let's just do f of x equals x. X to the first power. This is x to the 0 power. This is now x to the first power. What's the derivative of this? Well, again, I start with my intuitive idea. The graph of f of x equals x is this diagonal line. And the best part about that line is it's got the same slope everywhere. No matter where we are on this line, the slope is equal to 1. Up here, my slope was always equal to 0, and lo and behold, my derivative did that. Let's check. I know it's boring. I really do. It's tedious, but this is the only formula we have, unless you want to do the x minus f of x minus f of a over x minus a version. I like this h version a little better. So I plug in x plus h to this equation. I just get x plus h. This function says whatever you get out is the same thing you put in. So if I put in that, I get out that. Here I just put in x, so I get out x. What happens to these x's? Poof. So if the x's cancel, I'm left with the limit as h goes to 0 of h over h. But wait a minute, that's always 1, regardless what h is doing. This is a constant. The limit of a constant is that constant. We did it again. As I increase my degree, the algebra I do gets correspondingly messier. Let's look at x squared. I'm going to plug in x plus h, and that's going to give me x plus h squared. But now I need to multiply this out. That's not difficult. That's all done over there on my scratch paper. Again, I notice those cancel. Poof. And I'm left with 2xh plus h squared all over h. Oh, I can factor an h out of the top and cancel it. But now this h goes to 0, and this is, regardless of what h is, this is just 2x. Hey, we did something with an x cubed in it on Monday. Let's do an x cubed here. Again, we've already done one like this, but I'm going to do it again. F of x is x cubed. That means that f of x plus h is x plus h quantity cubed. So my derivative is x plus h quantity cubed minus x cubed over h. Now I have to multiply this out. I'm cheating because I've already done this. I have this already written down on my scratch paper. So I know what that is. But you could do x plus h times x plus h times x plus h and just do all the distributing. What happens? Oh, I forgot to write a limit. I always need my limit if I'm doing a derivative because a derivative is a limit. I have to have that limit there. So limit h goes to 0, x cubed plus 3x squared h plus 3x h squared plus h cubed minus x cubed all over h. Once again, my x cubed cancels. And everything that's still there has an h in it. So I'll cancel that. 3x squared plus 3xh plus h squared. H is going to 0. That means that term goes to 0. That term goes to 0. And the only thing that survives has no h's in it at all, 3x squared. Allow me to summarize. Here is our function. And its derivative. This is a constant. It is x to the 0 power. Whereas if I did x to the first power, I got a 1. If I did x to the second power, I got 2x. If I did x to the third power, I got 3x squared. And all of a sudden, my brain notices, wait a minute, this number is here. Now, 0 times anything is 0. So when I put the zero out front, that's zero. That's perfect. When I put the one out front, that's one as a constant. That's the same as 1x to the zero, because x to the zero is a constant. This 2, that's 2x, that's the same as x to the first. This is, these powers are all one less than these powers over here. I think I have a sneaking suspicion that if I were to do x to the fourth, then my derivative, the 4 should come down, and my power should go down. Sounds like a great idea. Looks like it fits our pattern. This is not a proof. This is a good hunch. So let's try it and see if our hunch is correct. The problem here is the algebra, which again gets pretty messy. This is where I mentioned my buddy Pascal and his Pascal's triangle. There's a fast way to do this based on Pascal's triangle. If we have a couple minutes, I'll tell you about it today. If not, I'll tell you about it tomorrow during question and answer day. It's not earth-shatteringly important. So, f prime of x is f of x plus h. Oop, don't forget to write the limit. Derivatives are limits. I can't forget that. 4x cubed h plus 6x squared h squared plus 4x h cubed plus 1h to the fourth minus x to the fourth all over h. Those cancel again. And everything that's left behind has an h in it, which means those h's will cancel with the h on the bottom. But we're still taking the limit as h goes to 0, so everything with an h in it gets turned into a 0. And that means the only thing that survives is my 4x cubed. It turns out that this hunch is always correct. Were I being a little more anal retentive, I would require us to go through and prove it will always work like this. Always, always, always. That is beyond the scope of this course. We would cover it in an introductory analysis course, not just an introductory calculus course. In general, if f of x is x to the n, then f prime of x is nx to the n minus 1. If I knew how to do Zoom emojis, I would have fireworks going off on the screen, but this isn't creative CCI for my Twitch stream, so it doesn't work like that. It might be a little important. I use this so much, it's called the power. By the way, it is at this point where I have the absolute pleasure of informing you that there is a wonderful thing hiding on our Canvas page. Let's go to the Canvas page. Ready? Calculus. In our web links section, down here Here's the link to the YouTube playlist. There are songs. Here's a song about epsilons and deltas by Tom Lehrer, who happened to be a wonderful mathematician at University of California, Santa Barbara, who unfortunately passed away this past year. He used to be a mathematician at Harvard until he realized he could make more money down at the bar singing songs about math. Calculus, the musical. I'm not kidding. This is legit. The Math Theater History of Science and Theater. They made a live show about calculus, and they have all the songs, not just for math, but for science. They've got a Nikola Tesla one, a Marie Curie. They've got a lot of stuff. There's a great set of songs here for Calculus the Musical that I heartily recommend. Um, the Power Rule is one of the songs. So if you need help remembering all these rules, there's a song for that. I would ask about questions at this point, but I'm recording, so you're not here to ask questions too. If you have questions, now is a good time to sit down with an email and start writing me up those questions to email me. So let's take a look at how we can use this. Because it turns out now if I want to do the derivative of, say, x to the 17th, rather than do x plus h, x plus h, x plus 17 times, I'm done in literal, oh, that's f of x, not f prime of x. I'm done in literally one step. Poof. F of x is x to the 100th. F prime of x is 100x to the 99th. All done. Oh, I love it. I love it. I love it. Do you know what else? It even allows me to do derivatives that don't at first look like powers. The correct answer is not that. That's wrong. But the derivative of x cubed is 3x squared. Right. But since this x cubed is on the bottom, there's a rule about powers that are on the bottom. How do you get a power that's on the bottom out of the bottom? Right, you use a negative power to do that. So this is really the same as x to the minus 3, which means when I go to take the derivative, it's minus 3x to the minus 3 subtract 1 minus 4, not minus 2. By the way, only the power goes in the bottom. This number stays on top. As long as I can convert my expression into x to a power, this works. 1 over x to the 6th, that's really x to the minus 6th. So the derivative is minus 6x to the minus 7. You will see the textbook does not like writing negative powers. So it's going to rewrite that to be negative 6 over x to the 7th. I don't really care. I'm perfectly happy with this. There are places where simplifying is useful, and there are places where it isn't. But we won't know until we get there. So there'll be some places where I tell you, yeah, we probably ought to simplify this because of what we're going to do with our derivative. But we'll explore those after we've got the how down a little more. Even things that you don't think of as powers automatically really are powers. A square root is a, there should be a chorus from all of you sitting in your dorms or homes or wherever. Oh, right. That's x to the 1/2 power. And that means that my derivative is 1/2 x to the 1/2 minus 1 is negative 1/2. Again, you'll see simplifying. A 1/2 power, though, is a square root. So you'll see that simplified like this. I'm not all that chuffed if you don't simplify. But that'll be the answer in the back of the book. That'll be the answer you get off of Wolfram Alpha. That'll be the answer you get out of ChatGPT, not this. So you have to be careful. Power rules work for any powers at all. F of x is the cube root of x squared. Well, that's a cube root. A cube root is a 1/3 power. But now I've got a power of a power, and that means I multiply my powers. And that means that my derivative is taken from x to the 2/3. Again, if I go through this process of simplifying, the 1/3 power goes on the bottom, but the 1/3 is a cube root. The 3 stays on the outside, and the 2 stays on the top. Yay! Power rule works for any power. Positive, negative, whole number, fraction, irrational numbers, ugly numbers. You can raise something to the pi power. I'm not going to, but you could. Again, at this point, I would say questions, but you're not here. So let me ask you about this. What if we wanted the derivative of 2x squared? What do I do with the 2? Hang on. I know what to do with the x squared. But when I think about the limit as h goes to, that's really a bad looking h, as h goes to 0, it would be 2x plus h squared minus 2x squared over h. Well, I can just factor the 2 out. And now by my limit laws, what do I do with the 2 here? I take the 2 and put it out here. A constant multiple can be pulled out front. This expression is the derivative of x squared. I'm going to use my different notation. This is 2 times the derivative of x squared. So to do the derivative of 2x squared, I really just do 2. Just like with a limit, the constant coming out, when I'm doing a derivative, the constant comes out. The derivative of c times f of x is c times f prime of x. Sometimes you'll see this written over here as cf of x all prime. I really don't like that notation very much. That's why I've been switching. But that means that just like with taking the power rule, I now have a rule for every constant multiple. I'm actually going to call that the constant multiple rule. Just like our limit laws. Hey, wait a second. Wait a second. If the rules I am doing are very similar to my limit laws, let me go back for a minute and think about my limit laws for a second. Oh, before I do, let me do another example of this. If I asked you for the derivative of 9x to the fourth, this constant multiple rule would tell me take the 9 out and do the derivative of x to the fourth. But we wrote that down just a minute or so ago. 9 times 4x cubed, or 36x cubed. I'm done. No crazy limit work required. Here's one that's a little sneaky. What is the derivative of 1 over 3x? Wait a minute, the x is in the bottom. The x is in the bottom, it should come up with a -1. But only the x moves. Derivative of, forgot to write that. Only the x comes up. I need to leave the 3 down there, and then my constant tells me to pull that out. But that's a power rule problem. Power rule tells me -1x to the -2. And that now goes back on the bottom. Yay! I have a power rule, I have a constant multiple rule, and they're very much like my limit laws. And all of a sudden, my brain says, I had a whole bunch of other limit laws. I wonder which limit laws still work. Turns out that one of my favorite pair of limit laws work perfectly for derivatives. The limit of a sum. How do I do the limit of two things? I do the limit of the first one, I do the limit of the second one, and then I add them. So if I asked you for the derivative of two things added together, the answer would be to do the first one and do the second one and add them together. The limit of a sum is the sum of the limits. Therefore, the derivative of a sum is the sum of the derivatives. If it works for adding, it works for subtracting too. Are you ready? Are you ready to see something that took us 20 minutes on Monday? What's the derivative of this? Wait a minute. F prime of x. That'll be 2 times the derivative of x. What's the derivative of x? Oh, I got to back up a couple pages. The derivative of x is 1. The derivative of x cubed is 3x squared. And those are subtracted because these are subtracted. The answer is 2 minus 3x squared. That's the same example I did on Monday using the limit definition that took us a full page. It now took one line and about 10 seconds. I don't have to do all those crazy limits. That is an amazing, wonderful piece of news. It makes my life so much easier. I can take the derivative of any polynomial by just looking at the pieces. The derivative of x squared is 2x. Leave the 7. The derivative of x is just 1, but you leave the 5. The derivative of 2, that's a constant. That's 0. The answer is 14x plus 5. I'm done. That's amazing. The derivative of 3x, derivative of 3x plus x squared minus 5x to the fourth. The derivative of 3x is 3 times 1. Leave the 3, take the derivative of the x. The derivative of x squared is 2x. Now we leave the minus 5 and take the derivative of x to the fourth, which is 4x cubed. 3 plus 2x minus 20x cubed. Derivatives tell me about the slope of the tangent line, right? Derivatives tell me about rates of change. Derivatives tell me a lot of information. And now I have a faster way of getting there from here. So here's a question similar to one we were asked in the homework. Find the equation of the line tangent to f of x equals x cubed plus x plus 1 at the point 1, 3. I have a point, which means all I need is a slope. But the way you get the slope of the tangent line is to take the derivative at the point P. This is the x value for the point P, so I really need f prime of 1. But rather than do a limit, rather than do the limit of f of 1 plus h minus f of 1 over h as h goes to 0, or the limit as x approaches 1 of x cubed plus x plus 1 minus 3 over x minus 1, those are disgusting. I'm going to do the power rule, the sum and difference rule, and I'm just going to come up with the derivative like this. The derivative of x cubed is 3x squared. The derivative of x is 1. The derivative of 1 is 0. I need f prime of 1. F prime of 1 is 3 times 1 squared plus 1. That's 4. Point, slope. Line. Y minus y0 equals m, x minus x0. Y minus 3. Slope is 4, x minus 1. Move that over and I get y equals 4x minus 1. There's my tangent line. By the way, we should graph this so that we can see that that actually is the right tangent line. So out comes my graphing calculator. I put in my equation, x to the third plus x plus 1. I put in my line, 4x minus 1. And I graph those. Here's my cube, and there's my tangent line. And just at the point right there where the two meet, their tangent. We could even zoom in and take a look right there. There's the cubic. There's my tangent line. Ta-da! As a matter of fact, now that I have the equation for the derivative, I can ask other questions about my derivative. At what x values Does the graph of y equals x to the fourth minus 6x squared plus 4 have horizontal tangent lines? Now again, your first reaction might be, yeah, how am I supposed to know that? Well, we could graph this. X to the fourth minus 6x squared plus 4. And we get rid of that other thing because we're not going to use it. And we go back to the standard window, option number 6, and we see this picture. A horizontal tangent line. Where does the tangent line look like it's horizontal? Well, it kind of looks like it's horizontal up here. And it kind of looks like it's horizontal down here and down here. So I'd like to know what those three x values are. How do I find those? Oh, we just said horizontal tangent line. What's the slope of a horizontal line? Again, there should be a chorus. The word horizontal means that my slope is 0. Slope of the line comes from f prime. And if I need f prime of x equal to 0, that means I need f prime of x. What is my derivative for this equation? Y equals, so y prime. What's y prime, ladies and gentlemen? Derivative of x to the fourth. Leave the sixth, derivative of x squared. Derivative of 4. 4x cubed minus 12x. I need that equal to 0. So let's set that equal to 0. And we'll solve it by factoring. Both of these things are divisible by 4 and by x. This factors. That's a difference of 2 squares. And these three things are being multiplied. If I multiply stuff together and I get 0, then either the first thing is 0, or the second thing is 0, or the third thing is 0. If 4x is 0, then x is 0. If x minus 2 is 0, then x is 2. If x plus 2 is 0, then x is negative 2. Let's check against our picture. If I am correct, and that's where my tangent line is horizontal, if I hit trace and put in one of these numbers, I should be at one of those spots. Well, if I hit trace, I'm at 0, 4, and lo and behold, I'm right at that top right there. If I hit 2, I'm down here. And if I hit negative 2, I'm down here. We found the right places. The places where we were as low as we could get. Wonderful. Oh, no, no, Dr. Sassmore, you made a mistake. Go back and look. I made a big mistake. Not huge, but it is wrong. Take out the red pen. I screwed up right here. If you pull out a 4, you're not left with x squared minus 4. You're left with x squared minus 3. This is wrong. But either 4x is 0 or X squared minus 3 is 0. If 4x is 0, then x is 0. Here I get x squared equals 3, which means I get x equals plus or minus the square root of 3. That's better. Square root of, trace. Square root of 3. That's at the bottom. Not 2. 2 is actually a little bit up. It's better if we zoom in. Oh, hang on, I got to adjust my window just a little. The bottom is here. Bottom is here. Trace. Square root of 3 puts me at this spot right at the bottom, whereas if I did 2, that's actually up here. And the tangent line's not horizontal there. It is horizontal there. Got to be careful. Arithmetic errors kill you every time. Again, at this point, I would ask about questions. If you have one, you should write it down. You should email me. This now allows me to take the derivative of any polynomial function, because a polynomial is number times power of x plus number times power of x plus number times power of x all the way down to a2x squared, a1x, a0. Repeated additions, I'll separate them with the sum and difference rule. Repeated powers, take the constant out front. That's exactly what this example showed me. A polynomial. I now know how to take all the derivatives of polynomials. Yay! That's a whole lot of functions for me to work with. Things like the height function, the distance traveled when we dropped an object, the position of a car on a track. We had examples like this. Now I can do this without having to do all those limit calculations. I can only do this on the sections of Chapter 3. I cannot do this for the homework you are doing for Chapter 2. But there are more kinds of functions on heaven and earth than are dreamt of in your philosophy, Horatio. To paraphrase Hamlet badly. Let's keep going. What if I have an exponential? And I'm going to use my favorite exponential. I'm going to use e to the x. E to the x. E to the x. That's not a polynomial. Since that's not a polynomial, I need to do something else. So if that's what I'm going to do, then I got to go back to my limit. F prime of x. Is f a limit as h goes to 0? F of x plus h minus f of x over h. That's the limit as h goes to 0 of e to the x plus h minus e to the x over h. I don't like that. But I remember some rules about exponents. If I'm adding powers is the same as multiplying. Multiplying those powers with the same base. So I'm going to put that in up here. Now that doesn't look like it's much better, except for the fact that there's an e to the x in both of these pieces. So let's take that out. Now notice, this piece right here, that has no h's in it. It doesn't give a flying flick at a rolling donut what h is doing. So as far as h is concerned, it's a constant, which means I can put it out there. Now here's an interesting note. This is a number. I don't know what this limit is. Right now it's 0 over 0. And 0 over 0 is hard to deal with. Because as h goes 0, you get e to the 0. E to the 0 is 1. But we picked this particularly. Since e to the 0 is 1, I can think of this like that. And that means this expression is the derivative of e to the x evaluated at 0. Wait a minute. That means when f of x is e to the x, f prime of x is e to the x times f prime of 0. We actually pick e to be the number that just so happens to work just right for e. This is equal to 1. And that means when you have f of x being e to the x, the derivative is also e to the x. E to the x is immune, invariant. It doesn't change when you take the derivative. Taking the derivative is ineffective on e to the x. To go with that, we have a cartoon. You use differentiate. Oh, come on, show me the bottom of the cartoon, people. There's the bottom of the cartoon. It's not very effective. You take the derivative of e to the x, you just get e to the x again. It never goes away. And that makes my life a lot easier. Now, please understand, there are still more kinds of functions involved. There are still other things. I've got all of trig functions, sine and cosine and tangent. I've got things that we haven't dealt with yet. You know, what happens if I do x squared times e to the x? Or if I did x squared over x cubed plus 5? How do I deal with multiplying? How do I deal with dividing? How do I deal with other things? Here's a function we used a lot. The inverse tangent. There's a lot more. And in every one of these cases, I want to develop a shortcut so that I don't have to keep using my limit definition. But that only works if I can actually do a shortcut. And I don't know that I can. But this is where I'm going to end Chapter 3, Section 1. Two important pieces of information. Tomorrow is question and answer day. It is question and answer day not just for our homework, but also for the exam. So you should be bringing me lots of questions, like questions about the review sheet. There will be a full key posted to that review sheet after you hand in the homework on Friday. So you'll have it all weekend to look at and study from because the exam is Monday. Unfortunately, since I am not on campus yet, I will not have office hours on Wednesday. If I get to campus early enough, my wife is going to be undergoing a procedure and I need to be there. I will email you. I will try and set up alternate office hours Wednesday evening and do them remotely. I'll set up an email. I'll send you something about that. I will also email you about this recording and about my reminder about tomorrow. So I hope you all have a good Wednesday, and I will see you on Thursday.